See, it works like that.
You probably never did anything that. I don't know.
When did you episode?
I did yesterday. I forgot to register, so I did yesterday.
I didn't know.
I know, I forgot like that.
It's you. Okay. We'll put that on the screen.
All right,
I got like 10.
let's get going on a cold Monday. How are you all doing? Good? Do you remember you have a quiz this Friday?
Yeah. Wasn't it's parts and analysis, right? That's what's all. It's everything.
Up until I would say end of carbohydrates lecture. Yeah. So protein characterization will not be part of it or anything. Yeah, I think, yeah, protein characterization will not be part of it. The other thing I want to say is your lab report supposed to be due Friday, which is approximate lab report. And since you have a quiz, I'm thinking to make it due Monday. Okay. The excitement in the room grew 10 times. Okay. All right. So, huh?
That's my rose ability. You just made my week.
Oh, glad. Glad to do that. So, okay. So will you let Gray know to update that due date from Friday to Monday, 11:55 p.m.? Okay, so this means you're going to study really well for your quiz and do very, very well on the quiz. Yep. I don't see excitement anymore. Yay. All right. Let's continue with the subject that we briefly started last Friday. And we are going to be talking about protein separation and characterization. And we provided some examples as to when protein separation is done. Can you remember any? When protein separation is really done? We talked about some protein ingredients, right? We said we separate and isolate to produce protein concentrates and isolates, like whey protein concentrate, whey protein isolate, soy protein isolate, concentrate, and the rest. So we usually separate the protein from different components in a matrix and then purify to a certain extent so that we can get the ingredient. So that is one application for protein separation. Since it's Monday and you forgot everything from last Friday, so here it is. Okay, so for food or food ingredient production, and then when we want to understand a new protein or a protein from a specific source, we isolate it and we characterize it. So that's when protein separation is done, is to isolate protein and to characterize it. Or when we want to purify an enzyme, which is a protein, it's an enzyme that we purify and then we use in kits to determine certain substrate, like remember the sugars or carbohydrates that we talked about. Previously, we use enzymes. So these enzymes are proteins and they are purified from different matrices. Or we purify antibodies or antigens to use in kits, like ELISA kits. So that is a second use or purpose. And then lastly, if we are studying the impact of different protein processing or extraction processes, we isolate and we characterize. Okay. So they're all relevant. Now, when a protein is in a matrix that has different components in it, could have carbohydrates in it, fat, other solubles or insolubles, we need to isolate the protein. So we base our isolation based on how proteins are different in different characteristics. So we know that proteins are different in nutritional quality, in functionality, but what we really rely on for isolation and separation is how they're different in their biochemistry. So understanding how they're different in biochemistry, then we can devise ways to separate them and isolate them. All right, so when we talk about the biochemistry of the protein, we talk about how they are different in their solubility in different solvents, like solubility in water, solubility in salt solution, or solubility in any other types at different pHs, for example. So different proteins have different ability to be soluble at under different conditions. So once we know this about the protein, then we can devise a separation using that knowledge about their solubility. We can also separate protein based on their thermal stability. So if we take in this here image, you have whey protein, beta-lactoglobulin specifically, and then casein protein. They differ in their thermal stability. Whey protein is very thermally labile, meaning it denatured at low temperature. So if I have casein and whey, and if I want to separate whey protein from the casein, I can heat up to 75 degrees, for example, for a few minutes. And whey protein will denature, aggregate, and separate from the casein that stays in solution. So that means we can separate based on the denaturation temperature of the protein. We can also separate based on size. Different proteins have different sizes. And if we have different components, the proteins also differ in size compared to other components. And I'll show you an example in a minute. So I can do membrane separation, for example, to separate proteins based on size. There are so many other techniques to separate proteins based on size, and we're going to talk about a few. Then charge. Proteins differ in charge, net charge, and their net charge is impacted by the pH of the system. So I can separate protein based on their net charge. I can also separate protein based on their adsorptive characteristics. So I will give you an example and remind you about hydrophobic interaction chromatography, anion and cation interaction chromatography, as well as affinity chromatography, for example. They are all adsorption based on adsorption characteristics. And we did say last time, if you remember, that whey protein isolate by the company is known as Agripor produces whey protein isolate by anion exchange. That's adsorption chromatography. All right. And then biological affinity to other molecules, like if you have antibodies to antigens or enzyme inhibitors to enzymes, and so on. The specific interaction of these components to each other. All right. So a lot on this one slide, but what I want you to remember is proteins are different in their biochemistry, and based on what we know about the biochemistry of the protein, we can devise separation techniques. That's all what I want you to remember here. Okay. So I'll start by giving you examples on separation based on solubility parameters. So salting out means that the protein will precipitate at high salt concentration. So when you have protein in water and then you add salt, the salt is going to interact with the charges on the protein, shield those charges, and prevent the water from interacting with the protein. And also, it will compete for water. So salt will compete with protein for interaction with water. So at specific concentrations, the protein will lose charge, will interact with each other via hydrophobic interaction, aggregate, precipitate. There will not be enough repulsion, net charge repulsion, so they will precipitate. All right, so let's think a little bit in simple terms. Let's assume in a solution I have 5 different proteins, A, B, C, D, and E. Each protein has a different net charge at neutral pH. And let's assume that protein E has the highest net charge, whereas protein A has the lowest net charge. Simple terms. So if I want to use salt solution, how would I separate C from a mixture of A, B, C, and D? How would I attempt a stepwise separation where I isolate C? Take a minute, please think about it, and let me know what you think we should do. Very simple terms. Go ahead, please.
Increase the concentration of salt over time.
Yes. So if I want to separate C and I know that it's in the middle of the charge, so what would I do as a first step? I will put in salt that is enough to precipitate A and B. Enough concentration of salt that will precipitate A and B that has the least charge. So a little bit of salt will shield the charges on A and B and cause them to precipitate. I would centrifuge, take the solubles. Now I have in my solubles, I have C, D, and E. Then I will add a little bit more salt that will be just enough to precipitate C and keep D and E in solution. But in order to devise such a protocol, I really need to know the net charge of A, B, C, D, and E, and have, empirical data, kind of experimental data that tells me what is the concentration of salt I would need to precipitate A and B. So there's a lot of knowledge that we need to have, but kind of like that's the principle, is you precipitate A and B, then you separate that precipitate, then you add a little bit more salt to precipitate C, and then separate D and E. Okay, that's kind of like in simplistic term, but of course we need to know a lot more about those different proteins, their charges, the salt concentration needed to precipitate each of them. All right, then a very easy one concept is adjusting the pH to the isoelectric point. What's the isoelectric point of casein? When you make yogurt, what would you want the pH to reach? Oh no. 4.6. Yes. 4.6. It's right there, isn't it? Why did you hesitate? It's almost wrong. Okay. So the isoelectric point of casein is 4.6. So in yogurt formation, what you do is you add your lactic acid bacteria, or the bacteria that produces lactic acid by converting lactose to lactic acid. I think Lactobacillus bulgarius. Okay. And then so the pH start dropping slowly when lactose is converted to lactic acid, and then the casein will coagulate and form that yogurt structure. Okay, so we have different proteins that have different isoelectric point, And if the protein is in a mixture with other components, other solubles at pH 7, and then we want just to take out the protein, then we can bring the pH to that isoelectric point. So there will be no net charge. The proteins no longer repel each other. They will come together via hydrophobic interactions and precipitate. Okay. We can precipitate proteins by using organic solvents, like acetone here. So usually the protein hydrophobic residues are hiding mostly on the inside of the protein. And then when there is solvent, hydrophobic solvent on the exterior, then the protein will interact less with water, and then it will start unfolding to kind of get its what do you call a hydrophobic component to react with the acetone. And therefore they won't interact with water, so they can be separated that way. Hydrophobic interactions aggregate, separate. And we talked about thermally treating the protein. So we can treat the protein so that it denatures, and when it unfolds, it will come together via hydrophobic interactions. Sometimes if you have 3 sulfhydryl groups, depending on the heat treatment and the pH, they can form disulfide interchange, and then the protein aggregate. So now what we have here is separation based on salt concentration, pH, organic solvent, and heat. So we are changing the solubility of the protein under these different conditions. So in summary, if I ask you explain 2 ways you can separate protein based on solubility, you can choose salt, pH, heat, and organic solvent. 2 of these. Okay. All right. Here's an example for an ingredient. Let's say we are going to produce either soy protein isolate or soy protein concentrate from a complex matrix. So soy beans are oil seeds. So the first step in the processing, so they dehull, clean, and flake, press to get the oil out, do hexane extraction, and then they get defatted soy flakes. That's the first step, remove the oil. For any protein extraction from a complex matrix, if we have high oil content, we have to remove it first. Then we know that soy protein is soluble at slightly alkaline pH, above pH 7, anywhere between 7.5 to 9.5. We can solubilize that. So in soy, you don't have starch, you have a lot of fiber. You have fat, fiber, protein as main components. Take out the fat, then you have protein and fiber. Insoluble fiber is not soluble. So if you put the protein or the flakes that is defatted, mix it with alkaline solution, protein will be solubilized in the alkaline, fiber will not. So you centrifuge, you get that protein in the soluble fraction, but you also have small sugars, oligosaccharides, some colors, some small salts, some small molecular weight solubles. You just want the protein, though, in that soluble fraction. So you go ahead and acidify to the isoelectric point of the soy protein, which is 4.5. So now in this step, you are separating the protein from all other solubles that came from soy flakes. You precipitate the protein, you wash a couple of times that pellet, you neutralize, and then you spray dry and you get an isolate of at least 90% protein. It's a very common ingredient in industry. All right. Let's say you want to do texturized vegetable protein, which is mostly made from soy. You don't need to purify that much. What you can do here is the soy flakes that have a lot of fiber oligosaccharides, and proteins, you can solubilize with alcohol or acid water. Fiber and protein will precipitate, and then small sugars will be gone in the aqueous alcohol solution. You dry, you get a concentrate of about 60 to 80, depending on how many washes, 60 to 80% protein. And this is what normally is used to extrudate and get your texturized vegetable protein. So these are two different industrial applications where protein separation is used based on differential solubility. All right, your favorite topic is ion exchange chromatography. Emma, like, no, it's not my favorite topic. I don't know what you're talking about. Okay, so proteins carry charge. Because they carry charge, we can use ion exchange chromatography that we talked about. And I told you, I promised you that I will be giving you a lot of examples about chromatography. And here's an application where anion exchange is used. And like I said, whey protein isolate by hydropore, formerly known as the visco, uses this method. So it's anion exchange. So your proteins are separated above their isoelectric point. Why is this important? Above, not below the isoelectric point. What do we know about isoelectric point? What's the charge above the isoelectric point? What's the charge below the isoelectric? What's positive? Below or above? Huh? So you have isoelectric point is 0. If you increase the pH, so now it's above the isoelectric point. Negative. Yes, so negative because you're going to give protons to the base solution that you're titrating with base. You're increasing the pH. So your protein is going to give protons, so it becomes negatively charged. Below the isoelectric point, it will be positively charged because you will have acid, and then all of these carboxyl groups will be protonated, and then the amine groups will be protonated, so you have positive. So usually for anion exchange, you separate the protein above their isoelectric point, and that's what is used for whey protein isolate production. You make sure that the pH above the isoelectric point, proteins are negatively charged, and they are separated based on their valence electrons. So the more dense the charges are on the protein, the more it's going to be retained. That's why in anion exchange, the whey protein isolate produced via anion exchange has more beta-lactoglobulin than alpha-lactalbumin. So because of the beta-lactoglobulin carrying more charge density than the alpha at a particular pH. And then, of course, remember that once you separated, you really want to get them out. So you change the pH, add salt to kind of displace your protein so that it comes out. Because you don't want it to sit there on the column for a long time. You want it to come up. All right. So just as a reminder, most commonly used protein separation are the polysaccharide-based resin, because they are made mostly for large molecular weight components. So polysaccharide-based resin is what is used, and then the OH groups are derivatized to carry a positive charge in case of anion exchange and a negative charge in case of a cation exchange. So one thing here is very important in red. PI of a protein is important. Whatever you do, when you run your proteins on a column, you want to avoid the isoelectric point. Why? So when you change the pH to elute, you want to avoid isoelectric point. Why? Yes, Al.
stable, sort of like stay in the isolation point.
If they're at the isoelectric point, they're going to foul your column. Have you heard of protein fouling of membranes and of systems? So if it precipitated on your stationary phase, it's so hard to get it up. It's just gonna stick there and cause issues of the protein remaining and hard to get up. So no matter what you do, when you do anion exchange or cation exchange of the protein, you really don't want to come close to the isoelectric point when you're changing that pH to elute the proteins. So it's a pretty good thing to remember. And speaking of that, take a piece of paper or a +2 and think of this question, write down answers, and let's discuss. It's so cold in this room, so it will do you good to think a little bit. It will warm you up. It seems like I'm not thinking today. I'm blue. It's just so cold. I'm turning purple.
Yeah.
Oh, it's time to think.
My hand is so cold.
All right, you guys, think. Less talking, more thinking. This is dangerous. Well, the wires are out. And when you think through it, if you know an answer or a direction, speak up. And I'm sure all of you will get there. Oh my gosh. You may or may not see the same question in an exam. Huh? Yeah. You're working together. I like that. Team effort. Team effort. Any thoughts? First question, would you use an anion or cation exchange? So you don't want the proteins that have a pI of 6 to 6.5. You don't want them. So you do not want them to interact with the column. Would they be positively charged or negatively charged at a pH below 6? They will be positive, both of them. All those, whatever, most of the proteins will be positively charged. But the protein you want has a different isoelectric point. So at, say, pH 5 or 5.5, would the protein of interest be negatively charged or positively charged? Negative. And the others will be positive. So what do? So you could, but what happens when you choose a cation exchange? Your protein of interest will leave the column with the void. So you don't want the ones, all proteins that have isoelectric point of 6 to 6.5, you don't want them. So you do not want them to interact with the column. So you choose a pH that they will remain positive while the other one is negative. So which ion exchange you would use, anion or cation? Huh? Anion. So if you choose a buffer at pH 5 or 5.5 and you do anion exchange, your protein of interest will be negatively charged and all the other proteins will be positively charged. You run your buffer and you inject your sample. The positively charged protein will not interact and will leave the column. Are you following me? At pH 5 or 5.5, your target protein will be negatively charged. All other proteins will be positively charged. So you choose anion exchange. All positively charged proteins will not interact with the column, will leave with the void volume. Yes.
Could you, just briefly go back over them?
What's that?
When it's cation, does that mean that the stationary is?
So what is exchanging? So it's a cation exchange, anion exchange. What's exchanging between the mobile phase and the stationary phase? The ions. So the charge, anion carries the charge of the one that you're exchanging. So anion exchange, that means you're exchanging anions. So to interact with the stationary phase, the stationary phase should be positive. Correct?
Yeah, so it's like basically opposite.
The opposite.
Yeah.
The stationary phase is the opposite of anion or cation.
Okay.
Because what you're exchanging is the ion. So anion exchange, all of your ions are negatively charged. You're exchanging negatively charged. So in order to interact with the column should be positively charged.
Yeah,
Make sense?
yeah.
Okay. It's fine. Yeah, absolutely. It's a complex thing to remember. All right, so you're following. So if we choose pH 5, the target will be negatively charged. All other proteins will be positively charged. I'll choose anion exchange. Okay. Yeah, so which proteins will elute in the wash? All of your proteins that you don't want, because they will be positively charged above 5. Okay, now your target proteins are interacting with the column. How would you get it out? After all those that you don't want left the column, they didn't interact, then now your target is interacting with the column. How will you elute it? Help it come out. What would you do? You change the pH. What do you do with it? you increase the pH. So now you have OH minuses that will displace your anion on the column. So now your protein will come out. You can also increase salt concentration. Both answers are correct. Huh?
Everything's like inverse of each other. You
Yes.
say positive.
Yeah, because OH minus is kind of the same charge as your ion, so it will displace it and interact with the stationary phase. No matter what, you do not want to go down with the pH. Why?
Because it'll stick even.
Yeah, because you're going to get closer to its isoelectric point. You do not want to get to the isoelectric point of the protein. In different cases, changing the pH in each direction might work. But in this particular case, you want to go up, you don't want to go down. And that is after you ensure that all those proteins that you don't want left but the void volume. Okay, good. Questions before moving on? Okay, alrighty. We are still with separation by adsorption, and this is a hydrophobic interaction chromatography. So in hydrophobic interaction chromatography, you rely on the hydrophobicity of the protein to interact loosely with the column via hydrophobic interactions. In this case, you put your protein in a high salt solution because you really want to remove the charges or shield the charges. You want all your protein to interact via hydrophobic interaction with the column. And we use this protocol, it's very commonly used if you have a lot of like carbohydrates and proteins and you really want to separate all of the carbohydrates, sugars, maltodextrin from the protein. So we run with salt, the protein is interacting with the column, then all of soluble sugars and other solubles will just come out in the void volume or in a little bit of salt solution. Will all come out. Then if I want to get the proteins out, if I'm just want to collect all my proteins, I don't care about separating them, I will just shift from salt solution to water without gradient, just switch from salt solution to water, all my protein will come out. Then I will collect my protein in the water. If I want to separate my proteins based on their hydrophobicity on the surface, then I can gradually decrease the salt solution. So if I start with 1 molar salt, I'll go down to 0.8, to 0.5, to 0.4, 2, until 0. Then I will get the proteins that have different hydrophobicity come out at different times. The most hydrophobic will interact the most, the least hydrophobic will interact the least, and I can separate my proteins. Okay. Questions? The last one here about adsorption chromatography is affinity, and this is commonly used if we want to purify antibodies or specific antigens for assays or enzymes. Also, it's very commonly used for enzymes, antigens, and antibodies. Very common. Also very common for specific glycoproteins used or needed for certain assays. So usually it's to purify for use as reagents. And this is based on a very specific interaction between the protein and a ligand attached to your stationary phase. So that interaction is like lock and key interaction, very specific, but non-covalent. So it's very specific, non-covalent interaction, hydrophobic, hydrogen bonding, ionic. So it's very specific at certain pH, temperature, salt concentration. So once your target interacted, everything else leaves in the void volume, then you change the conditions of the buffer. You can change the pH, the salt, for example, or you can add ligands, the same ligands that are attached to the stationary phase, you can add them in the mobile phase and get it out. Okay, this is just reminder to what we covered in chromatography, but here very specific to proteins. Okay. All good here? All right. Next, separation of the protein or purification of the protein by size. Dialysis. Who has seen dialysis before? Nobody in your lab? You don't use dialysis? We use it quite a bit in our lab, especially after an isolation that involves some sort of salt. Either the salt you use to precipitate the protein, or when you adjust pH, when you add base and then you add acid, what do you produce? When you add NaOH to adjust the pH to basic, and then you add HCl to adjust the pH to acid to precipitate the protein. Then you adjust the pH to neutral. What are you producing? HCl plus NaOH gives you, what's the chemical reaction? HCl. Okay, how tired are you? You're very tired. Why? Did you have a quiz today? Huh? Or is it just Monday? Just Monday? Bruh. What do you get?
Water and salt.
Yes.
Yeah. I said salt was in the water. You're saying it to hydration reaction.
Okay, so you get salt. So you don't want salt in your protein, whatever you're separating. It's not good for functionality. It's not good for purity. You don't want it. So dialysis is often used as a step after purification to get rid of excess salt. So if you haven't seen dialysis, tubes, what? Who's strong? Should open. Come on, Golden. One side should open. There goes my dialysis tube. Good thing this is not a good tube, it has holes in it. All right. Okay. All right, so once you have your protein in solution and there are quite a bit of salt in there, and you don't want salt, so you get these tubes. Okay, they're bad. So the idea is, oh my gosh, they're really bad. Old. Well, imagine this is longer. So you get these tubes, and then you put the clamp at the bottom of the one side, then you put your solution in it that has protein and salt, and you put another clamp on top. Oh my gosh, this is terrible. Okay. Then you put it in water or buffer. So what happens when you have salt in the tube and the tube is permeable? It has holes in it, small pores. What happens is osmosis, movement from high concentration to low concentration. So your salt will come out, but you reach equilibrium. You never get out all your salt. After a certain period of time, the salt concentration in the tube is equal to the salt concentration outside the tube. What do you do next? You still have a lot of salt in your sample. What do you do? Logic. you throw away this water and put fresh water. What's happening today? You're not with me. Okay. Throw away that water, you put fresh water, and then you let it reach equilibrium. And you keep doing that until there is an infinitesimal amount of salt left in the tube, and then you're satisfied. You take your protein solution and you continue with your process. So dialysis is to purify from salt and small molecules. You might have glucose there or lactose or what have you. You don't want it in your sample. So you can get these tubes with different sizes of holes. You can get 500 Dalton, 1000 Dalton, 3.5 is what we use, kilodalton, and you can get 10,000, you can get 20,000. It really depends on the size of the protein you want to retain and the little compounds you want to get out.
Good question. What
Yeah.
prevents the proteins from coming back out from that?
The size of the pores.
So they just can't go in, or do you start?
So you just put your solution,
Oh.
only salt can come out because the small size.
Okay.
The proteins usually are larger than the salt, so they will be retained. We call them the retentate, and we call the salt permeate. So they go out, they permeate through the pores, and the protein stays inside. You can enhance such process or membrane filtration by using tubes that have filter membranes in them, and you can add centrifugation. So you add a force to push through your solution that has those small molecular weight to kind of enhance by applying force. So you enhance the separation. And sometimes this is used to separate, for example, if you do a hydrolysis, you get your protein and you hydrolyze, and you want to separate the peptides from the large proteins. You can choose membranes with different pore size and get all of your peptides that you are generated. You can get it through the permeate, and then retentate will be the large molecular weight protein that you probably don't want. Another process we use on a lab scale, this is a bench scale, but there's also pilot plant. Have you been in the pilot plant? Did you see membrane filtration in the pilot plant? That's exactly it, but on a small scale in the lab. We also have cassettes of that have membranes with different pore size. We have a pump that would pump through your sample, and then you will have retentate that you're collecting, and then whatever goes through is the small molecular weight substances you don't want, and you do multiple washes with water until you get out almost all of the small molecular weight. In the pilot plant, they measure total solids in the permeate, and they stop their ultrafiltration diafiltration, they call it. Diafiltration is kind of like dialysis, but not really, but you're adding water and diluting. So they keep adding water and running through the membranes, and then they measure total solids in the permeate. Once they reach zero, then they say, okay, all the small molecular weight are pushed out. So, and it's a common thing we do for protein isolation and purification in the pilot plant. All right. One minute. So the separation by size, you choose different sizes of membrane. You probably heard of reverse osmosis, nanofiltration, ultrafiltration, microfiltration, and traditional filtration. Usually, it depends on the size of the molecule. So reverse osmosis is when you purify water and get salts out. And then nanofiltration, you get molecules like lactose that you would retain lactose, for example. And then the ultrafiltration is mostly where the proteins lie. and you can retain the proteins with ultrafiltration, and microfiltration, you can retain bacteria and fat. So this is a system in milk. So if you use microfiltration, you can, everything passes and you can retain the fat and bacteria. Then if you put an ultrafiltration membrane, you can retain the protein, lactose, minerals, water will pass. If you put a nanofiltration, you will retain the lactose, and then minerals and water will pass. If you put reverse osmosis, only water will pass, and then you get rid of the salt. So that's a series of purification using membranes of different pore sizes. With this happy note, I can let you go, and I'll see you on Wednesday. Free to go. Yes, please give them to you. And remember, the fiber question is due Wednesday if you want your +5.
Yeah. He doesn't even feel like.